So it's really my great pleasure and honor to introduce a dear friend, Professor Rodney Brooks, one of the most visionary researchers I know. Rodney Brooks is the emeritus, despite his young age, Panasonic Professor of Robotics at the Massachusetts Institute of Technology. His undergraduate degree was in mathematics in Australia. He was born in Adelaide. And his doctorate is in computer science from Stanford University. And his research has spanned many areas of computer science. Actually, he has developed many issues about Lisp, computer vision, robotics, and artificial life. As you will see during his talk, what characterizes Rodney Brooks, in my opinion at least, is elegance, audacity, and impact. During his thesis at Stanford, he developed a system called acronym using a very elegant mathematical object called generalized cylinders or generalized cones, basically a cone which changes its shape as you travel along its axis. It was used to model 3D objects and recognizing them from 2D images. That was in the early or the late 70s, I would say. And as you know, it's a very daring endeavor indeed, because even today, we don't know how to do this exactly. However, he has used also these representations to work on robot motion planning. He worked also on space modeling, navigation, and robot localization in the early 80s, before boldly deciding to turn artificial intelligence upside down by building robots with simple behaviors that increasingly grew complex. That was the period of the famous subsumption architecture, and the papers, which titles are self-explanatory: Elephants Don't Play Chess, or Intelligence Without Reason. He also built, among other machines, Cog, a humanoid robot that was able to learn more and more complex behaviors. I will not give an entire list of the systems and robots he built. I have to leave some room for him to speak. He became the director, first of the Artificial Intelligence Laboratory and then of the Computer Science and Artificial Intelligence Laboratory at MIT from 1997 to 2007. But his impact wasn't just scientific and an impact of leadership. He indeed was co-founder of iRobot, which is in the NASDAQ. And he held various offices in this company, including Chairman, Chief Technology Officer from 1990 to 2011. There are over 8 million deployed robots based on his work. Maybe some of you have one Roomba at home. And this is a direct, not young son of Rod, but a direct offspring of his imagination. Recently, he founded a new company called Heartland Robotics in Boston. This company aims to revitalize manufacturing, back to manufacturing, through new sorts of industrial robots that ordinary line workers can use directly. And he will certainly tell us more about this exciting new challenge. Rod?
Thank you, Raja, for that introduction. Thank you, Jean-Paul, for inviting me here, and thank you all for being here today. I'm not going to talk today in any deep technical way. I'm going to talk more about how to get robotics and what the challenges are getting robotics into applications in the everyday world. how to get your research to have direct impact on the world. And lots of the talks have talked about that. Mike had a bunch of examples yesterday. But I want to talk about the strategies people use to get their ideas out into the real world. And the critical, the most common strategy people use is this one. They hope. They have this good idea and they just hope it's going to have an impact on the world. An alternative is to, and then you sort of complain that it isn't happening. Why isn't anyone using my idea? Well, it's a great idea. Why isn't it used? An alternative way is to go and register the idea with your institutional licensing office, and I think that's pretty much the same as hope. It doesn't really have an impact on the world. Another way, as researchers, as academics, is to have commercial sponsors of the work, and therefore try to get the ideas to have impact that way. I've worked a lot with commercial sponsors as a lab director, and I think the key to actually having impact is to have personnel from the sponsoring company in the lab, because ideas don't migrate by themselves. They need people to take the ideas and to push them back and to become champions of them back in the home company. Without that movement of people, I think it's very hard for an academic idea to really have an impact on a company. Some people say, well, that's a bit, some people feel uncomfortable because at one end they're not getting financial reward for the ideas, and the other end is having a commercial sponsor sort of skewing your science or technology. And so there's some moral questions there in both directions. Another way is consulting for a company, and again, that's often you might get brought in as a consultant at a high level, and the high level people think this is going to be really good for the company, but to get it actually to have an impact, you have to work closely with the people who are doing the real tasks on a day-to-day and have them buy into having you as a consultant. And the other way is to start a company around your idea, and that turns out to be a lot of hard work, and often you end up leaving academia if you start a company, as I have in my most recent company. But I think as academics, and I'm speaking in the we of academics because most of us who've been talking at this conference are academics, we as academics tend to overestimate the importance of our ideas and underestimate the difficulty of making them real. So a PhD thesis turning into a commercial system, you've got this brilliant idea, and so some people think that's the idea. I can go and raise venture capital, I can sell the idea, people will love it, it's fantastic. But really, that's only 10% of the problem. There's another 90% of extra work after the PhD thesis to make it real. And now that you've done this 100% of work, you've got a robust demonstration that you can use to go and raise money, and then do the next 90% after that to make it into a real product. And as engineers or scientists, everyone thinks that's now we've done it. It was 100 times harder than we thought originally. Now we've got it working, it's great. But then there's another 90% after that. And that is the manufacturing, the marketing, the sales, the distribution, the dealing with returned product, service, sustaining engineering. And so what starts out as a key, brilliant idea has to be decorated with hundreds of other people working on it for many years to turn it into something real. That said, I still think it's a great time to do lots of robot companies. But there is a lot of work, and it's not just the idea, it's the other stuff that comes around it. Recently, we were hiring a VP, Vice President of Marketing at my company, and one of the senior engineers said, I have no idea why we would need a Vice President of Marketing. Just so there's a gap between engineering and business. So I'm going to tell some stories from robot-specific attempts to get ideas to have impact on the world today. And then I'm going to contrast differing views of how things work in the world between academics and non-academics. So the first question, Matt was trying to define manipulation. Ask the question, are we ready for large-scale impact from robots? They're on the horizon, but can they have a big impact? And I think they can, and I'll show you some examples. Those of us who have grey hair remember the old days when computers looked like that. They were very large, expensive machines, and ordinary people couldn't touch them. They were in special rooms, and you didn't program them directly. Certainly if you're a person on the street, you'd never seen one, never touched one, never interacted with one. People were not allowed to be near the computers because actually people were too dangerous for computers because they all smoked, and the smoke particles got in the disk drives, so you had to sort of keep the people away from the computers. But then, in around 1980, with the PC, ordinary people got to touch computers, and out of that came a flowering of all sorts of forms and applications, and it's completely transformed our world because ordinary people can touch computers. And now, you know, we all carry around very powerful computers, much more powerful than the one in the picture there on the left, with much more storage and connected to the networks around the world. We carry everything in our hand. Robots, and especially industrial robots, are sort of like the mainframes of old days. Ordinary people can't touch them not because people are dangerous, but because these robots are dangerous, and you have to keep the people and the robots separate for their own safety. But what if ordinary people could touch robots? And in fact, over the last dozen years or so, they can. And we've seen a number of people yesterday showed the Da Vinci system on the top left-hand corner, where the robots touch people and the surgeons touch the robots. On the right is the Kiva system, which is a warehousing system, recently got sold as a startup in Boston, recently got sold to Amazon, where the orange things below are robots that carry shelves around up to a person who then picks out objects at a fulfillment center. So the robots do the task they're good at, which is navigating, and the person does the task that they're good at, which is grasping an unknown object, because we can't get our robots to do that yet. In the middle is the Roomba, home cleaning robot, and on the bottom are some military robots. Some robots in Iraq doing bomb detection. This is a robot that was brought into a depot in Iraq by a soldier. It got blown up, which is much better than the person getting blown up, trying to deal with the bomb. But you see on the back here that the person whose robot it was had been keeping track of it, gone on 17 improvised explosive device missions, 1 vehicle-based improvised device, and 1 unexploded ordnance. So it had 19 successful missions before it got blown up. The guy brought it into the depot and said, "Can you fix it?" And they said, "No, we can't fix that, but we'll give you another robot." And he said, No, this is Scooby. We've been through a lot together. I want Scooby. Scooby's my buddy. And that was a surprise to us, but there was a bonding between people and robots, which we had not expected. And then on the right here, this is a newer sort of robot, the SUGV, Small Unmanned Ground Vehicle, which is now getting slowly adopted across the US Army, 1 robot for every 9 soldiers to go in ahead of soldiers. And there's a lot of people with moral questions. Is it right to have robots? Is it right to have robots in the military? To me, the answer is that it can be more moral than having people. The old way of dealing with explosive devices was to take the youngest member of the troop, put them in a bomb suit, tie a rope around them to drag them back if they got injured or killed, and send them out to poke the bomb with a stick. That's no longer allowed. The doctrine in the US military is you have to send a robot to go out, so you don't put a person's life in danger. And likewise, if a robot goes in first, the phrase that I like is a robot can afford to shoot second. It doesn't matter if a robot gets shot. And so you don't have, if you're a young soldier going into an unknown area, you're scared out of your wits and trigger happy. Sending a robot in to look around and get the situation can actually calm the situation a lot more than sending people in. So over the last 10 years, there's been tremendous uptake of robots in the US at least. In June of 2002, there were 0 robots, ground robots in the US military. There's now more than 12,000. In June of 2002, there were 0 robots in people's homes. There's now more than, as of January, there were 7.5 million, and it's increasing at 1 million per year. So tremendous uptake of robots that ordinary people interact with. These are some of the home robots that iRobot, a company that I founded, make. There are other companies working on them. Some of the military robots, including underwater robots. This is the PackBot, which is about a 30-kilogram robot. I'm going to come back to that later. This is a 200-kilogram robot, the Warrior, which I'll come back to also in a little while. But why have things taken off? Why over the last 10 years or so? Well, computation and sensors have gotten exponentially cheaper for 50 years, and I'm going to talk about that in a little detail, because I think that's been really important for us. Research in computer vision and SLAM, simultaneous localization and mapping, have made major strides in the last 10 years, and so you can do stuff with these robots. And for certain tasks, robots have passed a usability threshold that makes them useful to untrained people, and this is the key. We can, as robot researchers, we can make all sorts of algorithms and clever demonstrations, but it's when ordinary people, untrained people, interact with the robots that they really become useful. That's the key. So the first of my things there was computation sensors have got exponentially cheaper. I just want to talk about exponentials for a little bit, because I think we forget how important they are. Exponentials in information technology have been critical to robotics. This is the magazine article from 1965 that Gordon Moore wrote, from where we get the phrase Moore's Law, about putting more components into integrated circuits. It was a few-page article in a magazine. And the abstract is quite straightforward. This is 1965, and in the abstract he said, by 1975, we may get as many as 65,000 components on a single silicon chip, which was a bold prediction. But the first 2 paragraphs were even bolder. This is the first 2 paragraphs of this little article, and he predicted integrated circuits will lead to such wonders as home computers. This was in 1965, when a computer would fill a large room and cost over $1 million, and he was predicting home computers. Automatic controls for automobiles, and Mike, I'm sure you had a car that was built in the 50s or even in the 60s. There was hardly any electronics in cars back then. Today they're packed with electronics, but there was nothing much there. And this is the best one. He said personal portable communications equipment. He predicted this in some form. In the paper there was a cartoon, and this is the cartoon. And I asked Gordon a few years ago, I said, Gordon, was that cartoon you're doing? And he said, no, he opened up the magazine and the cartoon was just there. But you see someone selling handy home computers right next to cosmetics. My guess is that the cartoonist was sort of lampooning or making fun of the article, saying home computers. Sure, we'll sell them just like cosmetics. But the joke is on the cartoonist, because that's in fact what happened. This is the key graph in that paper from Gordon Moore. He had 4 actual data points. This was the null data point. He plotted 4 points on the number of components on a chip, the logarithm of them against the year, and from those 4 data points, he just extrapolated a straight line on this log linear paper, and he got to 2 to the 16th in 1975, and so he said, yeah, by 1975 we'll have 65,000 components on a chip. That was the depth of the prediction, but it turned out to be true. So I have an equation in my talk. I said it wasn't technical, but I have an equation. What defines an exponential? It's this differential equation, that the rate of change of the amount of stuff you have is proportional to the current amount of stuff. That's what makes an exponential. So is that why these chips got denser and denser? Was it a self-generating exponential? You know, was the power of computers getting far better and better so you could design better and better chips? Well, it wasn't in play in 1965, because the first computer that used integrated circuits was the Apollo guidance computer for the lunar lander, and the Block 1 version of that was first built in 1968. It had 1 gate per chip. The flight version in 1969, there was exponential growth in that year, had 2 gates per chip. And it's an interesting thing about ordinary people and computers. There was a big fight within NASA about whether the guidance computer should be in a sealed box. The astronauts wanted it in an unsealed box so they could fix it if it broke on the way to the moon. And engineering good sense prevailed because people realized that having the box openable would lead to more failures than having it sealed. So it was the first sealed system that flew on inside a space vehicle where the astronauts weren't allowed to touch it. So that gets back to the ordinary people, astronauts in this case, using computers, had to change the way they thought about how they interacted with them. So this equation didn't make the exponentials happen in 1965 for integrated circuits. I've got a longer talk where I derive what I say are 3 ways that you get exponentials in technology. One is the rate of improvement is proportional to the current level of adoption. And that's what's happened with Facebook and networks in general. That's certainly true. Another law is the existence of the law tells everyone what level to aim for. And once Moore's law had been established, people expected the number of components to grow on a chip exponentially. They expected the number of bits of memory to grow. So I know in Silicon Valley, and I'm sure in Japan during the 80s and 90s, as engineers at chip companies came into their desk every morning, they passed a graph which predicted how many bits of memory you had to have on a single chip over what years. So all those engineers knew what they were aiming for, what they had to hit, the target they had to hit in 3 years, the target in 5 years, when the current technology was going to run out, how they had to develop the new technologies. So the existence of the law told people what to do. But then the third one, and this is where robotics comes in. Someone else is driving an exponential, and you get to hop on it for free. And that's where we are able to, one of the reasons that robotics has gotten so much better, because other industries have driven exponentials, and robotics has been able to take advantage of them. Professor Inoue, if you still had your 4,096 word computer and 42 microseconds to do a multiply, it would be very hard to have those humanoids doing all those great things you showed the humanoids doing. It was that exponential growth in computation power which enabled you to do other things. But I want to say another word about exponentials, because people, I think, in technology, think everything's going to be exponential, and venture capitalists in particular think this, and I think they've made some fundamental errors recently. Information technology has a special relationship to physics. All digital instantiations in information technology are based on a 1-bit abstraction of a bulk physical property. It's a yes-no. It's a 1-bit abstraction of some bulk. And actually, in Gordon Moore's little paper, he speculated at the end that although the number of components on a chip would grow, he said the battery power will not have exponential growth for this very reason, because battery power doesn't deal with the same bulk property. It's the number of electrons you can fit is important for battery power. It's not important for a bit. So if you have a pile of blue versus green sand, you can have these piles, you can look at them, yeah, that's a blue pile on the left and a green pile on the right. If you take away half the stuff, it's still a blue pile of sand or a green pile of sand. You take it away again, it's still a blue pile of sand or a green pile of sand. It's a 1-bit abstraction. You can keep halving and halving and making these piles smaller and smaller, until you get down to just 1 grain of sand, and then it runs out and you have to go to multi-core. That's a computer science joke. So the physical bulk can be reduced while maintaining the abstraction. That's the important thing. And as a result, we have technology exponentials all over the place based on that information technology abstraction of 1 bit of a bulk property. And then the information technology exponentials beget other exponentials based on them, where people are riding on the IT exponential. That's not true in other domains. Here's a favorite industrial robot, say, you can, if you shave off half the matter here, half the mass, well, it's a well-built robot. It will probably still work. But if you shave off another half, and it's down to a quarter, it's going to start to get compliant in ways it shouldn't. And by the time you get to the third halving of the physical bulk, this robot isn't going to be able to carry the load that it can carry now. You can't just exponentially, over time, decrease the mass. I think that where venture capitalists, at least in Silicon Valley, went wrong recently was they were used to having so many exponential growth stories that they started talking about green tech and energy and thought, oh, we know how to make things get better and better quickly. We'll start investing in energy systems and green tech, and it didn't have the exponential growth that information technology had because it relies on physical bulk. So someone else is driving an exponential and you get to hop on it for free. That's important, and if you're trying to do something in turning a demonstration in a lab into a real product out in the world, it's worth thinking about where is there an exponential that I can ride, that I can get to make my system better. And exponentials do have a great impact on robots. You know, a few people have shown their old videos. This is the first robot that I professionally worked on at the Stanford AI Lab. It was really Hans Moravec's PhD thesis, but every night at midnight, I would help him get it set up. And there's the robot. We'd set up some obstacles. People were going home, so that the mainframe computer had time available, and this robot would then drive across the room. You see, there's the flashes are because this was made on 16mm film, and the film's being stopped. There's a single camera there being slid from across the robot because it was a $50,000 camera and there was no budget for a second camera, so to get stereo vision, he slid the camera across. It would take some images, process them for 15 minutes, and then move a meter. So on a good night, between that wall and this wall was 6 hours to get across the room, 20 meters in 6 hours at the Stanford AI Lab. So you know, Gordon Moore had 4 data points. I'm not as good as Gordon Moore. I only have 3 data points. But this is the cart at Stanford in 1979, 20 meters in 6 hours. This was one of my robots. Ian Horswell was the student at MIT, gave tours of the AI lab in 1992, and it would run for about 6 hours on a single charge and go 2,000 meters. And then this is Sebastian Thrun's robot Stanley, Sebastian from the same lab as the cart, the AI lab at Stanford, 200 kilometers across the desert in 6 hours in 2005. And if you plot those 3 points, you see that there's 13 doublings, 2 to the 13th, in 26 years, so a doubling of capability every 2 years. So there's a nice exponential story there. But I think it was largely driven by the lowering cost of sensors and the increase in computer power. This is a $50,000 camera. It wasn't a great camera. Actually, about 2 years ago, I saw a web camera available for $2.99. I couldn't resist, so I bought half a dozen of them. And included the USB cable for that $2.99. And you know, looking at it, trying out of the images, it was a pretty lousy web camera. But it was way better than that $50,000 camera from 1979. And it was only $3. So we have all been lucky to have these exponentials going right when we're working on robotics to help us along. Now, why do robot companies make sense today? The exponentials let you do stuff, but why do they make sense? I think there's a customer pull and a technology push. From the customer pull, there's many service jobs that people just don't want to do. You know, there's an incredible unemployment in Spain right now. Oh, so there must be lots of jobs for people. Where is the highest, this was interesting data for me, the Roomba, the highest rate of sales in the world is in Spain. Almost 30% of all new vacuum cleaners sold in Spain today are robot vacuum cleaners. So it's not that there's no one around who could do the cleaning jobs. People are unemployed, but they're still buying robots to clean their apartments. People don't want to do service jobs anymore. There's a pull for rehabilitation and deficit assist, and we've seen some examples of that in the talks. The demographics, and I'll come back to the demographics, turning the elder-younger ratio upside down. And it's not robots to help the elderly people or to take care of them that are important, but to do the jobs that there just aren't enough people to do now. We need to be more productive to compete globally, and robots can help there. And in the US, certainly, there's a large hostility to undocumented workers, but no one wants to do the jobs the undocumented workers do. From the technology push side, 45 years of Moore's Law has been really good to robotics. We're now able to, not everywhere, but replace mechanical precision with computation in lots of places in robots, so we can get by with cheaper parts that aren't reducing in cost, but use computation to overcome them. And then we have things like statistical machine learning. We saw it just in Matt's talk, as enabling us to do new things that we couldn't do before. Massive data sets on the web for machine learning, and SLAM has been a real success story for robotics. And finally, so those are there, and finally we're getting better user interfaces and user experiences so that ordinary people can use robots. And the cheap sensors and computation I already mentioned. But as we build robots, it turns out that they being the customers, are not us being the robot researchers. The customers are different from the people who are inventing the robots. If you really are building a robot product, no one from your company will ever see or touch the vast majority of your produced robots. When we were starting to build military robots at iRobot and starting to get into production, Admiral Joe Dyer came to head up that division. Three-star Admiral, former Chief Test Pilot of the Navy, former Chief of U.S. Naval Air Command. He said the happiest day in his life was when iRobot shipped a robot without a PhD touching it. Because if you're going to scale up, it can't be us involved in the production of the robots or the training. There'll be no one from the development team to tweak the robots. They have to go out there and work. And Mike talked about some of his companies which have produced hundreds or even thousands of systems, and it's not your students who are going out there with the product. They have to work out of the box. There'll be no one from the development team to hold the user's hand as they interact with the robot. A lot of the robots we play with, and even in demo days at Carnegie Mellon, the researchers are still around to tweak things and fix things if they aren't quite working. It's very different from an out-of-the-box experience in another country and just working. No one will be there to explain anything. The users care about getting their tasks done. That's what the user of a robot cares about. They don't care in general whether it's a cool robot. And they don't even care about whether it is a robot sometimes. That's not important to them. They want the job done. That's a different attitude than the researchers have. But real robots have real users. That's the point here. So, and things are different. These are some models of the iRobot Roombas. The first one, this one, had a bunch of different buttons for the size of the room, and it had a rocker switch over here to switch on and off. Straightforward idea. Countless service calls. Which way is on, which way is off? What do these buttons mean? So this is the latest version. It has one button in the middle. There's no on-off switch. It's just a button that says clean. The only thing you can do is press it. It doesn't have state. That's the thing you can do, and that makes it work. So getting there and experience with real users made us realize we had to change some things. But then users always surprise us. These are some of the things that people have done with their Roombas, which was not expected. We didn't know they were going to be part of a humanoid robot, and everyone wants them to deliver their wine. But more interestingly, this was a great example, a real eye-opener for us. We have these things called virtual walls, which are, put out a little infrared beam, and there's a little instruction on how you put them to block off a corridor so the robot won't go out of the door. So you put this wall there, this virtual wall, and it's an invisible beam, and it blocks it. Straightforward. Okay. So one of our people was in Denmark last year at an elderly person's home, where they were very proud that they were using robots to clean the home, to cut down the cost of healthcare workers by having robots clean this home that housed about 50 people. And the woman, he asked her just to watch, just to observe how a real person was using this robot in a commercial setting. And what he found was that the woman who did it every day would switch the robot on and then put the virtual wall on top of the robot and have the multiple ones go off and do their stuff. She didn't know what this did, but it came in the box, so it must have something to do with the robot, so she put it on top. And now the interesting thing was, this made these robots, he had two of them, it made them into Bratenberg vehicles, and they could detect each other coming, and they sped away from each other. So it actually had this funny use that she didn't realize and wasn't the intent, but that's what happened. So real users do stuff with your products and use them in ways you will never guess, and it doesn't help, being really smart about this. So we had these robots and still have them in Iraq and Afghanistan, dealing with improvised explosive devices. And after our robots, there's other companies. Kinetic, British company, has Foster Miller, a subsidiary, which has also robots in Iraq and Afghanistan. And after we had a few thousand robots there, word came back from the field that the iRobot interface, to use a technical term, sucked. The users didn't like it. It was this, this is the so-called laptop, except it's bomb-proof, so it's really heavy. It will crush your lap if you put it on your lap. But it's got these great joysticks here, and it's got a menu system on the screen, and you can do anything with this interface. You can, control the robot. But the word came back and said, the interface sucked. The response of one of our engineers at iRobot, who remain nameless, Pavlo Rudichevich, he, in response to this, he said, well, we need smarter users then. Oh, okay, we'll just tell the army to enlist different people, maybe with PhDs from MIT, to go out into the field in Iraq. Yes, Pablo, that will work. That wasn't the answer. The right answer was to adapt to the users, and this is the adaptation, to get a game controller. Now, the engineers thought this was dumb, because with the game controller, you only have about 85% of the capabilities of the robot. But zero training, 5 minutes of playing, and all the soldiers could use the robot and get 85% of the capability. It turned out they'd never gotten 85% of the capability with the old user interface. So it was dumbed down in a way, but it was became a more effective tool. And I think that's true for all of us with our smartphones. The first version of the iPhone came out, didn't have cut and paste. And people said, well, you have to have cut and paste. That's terrible. But they sure sold a lot of phones without cut and paste, and people used them, and it was effective. And it was only later, when people got used to the interface, that cut and paste came in. So adapt to your user. It's very important. I'm not going to say in great detail, because we just haven't said in great detail what we're doing at Heartland Robotics, but this is what we have said. We're building robots that are designed for ordinary people to work with and to make them more productive. They're easy to use, flexible, unbelievably inexpensive, built in the USA. And that's what we're doing with robots in general, in particular with manufacturing, putting robots in the vast majority of factories which do not have robots at all, and make them easy to use so workers can be more productive. And to us, the fundamental belief is that the ease of use, setup, interaction, training are critical to the adoption of robots. If they're not easy to use, people are not going to use them in factories. If they're low-cost devices, if they're too much trouble, they won't get adopted. The user experience is critical to the robot's success. But this leads to, well, who are the users? And for any robotic product, it's actually multiple users. I'll come back to, some principles first. There are multiple different users with fundamentally different personas who are going to use the robots. Users will not be happy with unauthenticity. This is a word that I made up. I'm going to explain unauthenticity in a little bit. And a person, it turns out, can do much better perception non-cognitively than most perception algorithms. So if you can use the person to do perception for you, it's going to be easier. So this is getting back to Professor Inoue's robot person partnership, because people are so much better at perception and so much better at manipulation than our robots are. And if a robot is going to be used outside an academic setting, then the users are not going to be us. They're going to be different sorts of people. So the multiple users along orthogonal axes. When someone buys a robot, there's someone who makes the buying decision. That's a user. There's someone who unpacks and sets up the robot. That's maybe often someone different. The person who tells the robot what to do, maybe yet another person. The person who tweaks it on a daily basis, maybe yet another person. And the person who interacts with it as part of their job, maybe another person. So these are all different users who all work with the robot. And these people, independent of what their job is here, may have very different styles. When you go out and talk to people and ask them about technology, you get technophobes who just think all technology is horrible. I don't want to deal with it. There's a gadget person who thinks any technology is great and they want to play with it and interact with it. There's people who say, just give me the recipe. I don't want to understand how it does its job. Just tell me what I have to do and I'll do it. And people, what the hell am I going to do with this robot? Why do I need a robot? Some early complaints we got from Roomba users were it took people longer to clean their house with the Roomba than it did themselves, because you have to sit and watch it for hours and hours. And then people will speak different languages. They'll have different levels of literacy who interacting with the robot. And here's one. In lots of jobs, they'll be wearing gloves, so touch screens don't work anymore because they've got gloves on for their job. So you have to think about who's actually going to use it. It doesn't matter how great an idea and how sexy the demo is in the lab. You know, people are going to be like Mark Rabot. They're going to come and drive that robot harder than you ever did. And you're not going to have control over them. So I want to talk about unauthenticity with some examples. If a robot looks like Einstein, it better be as smart as Einstein. So when you build your robot, and people will maybe know the reference that this is too, when you build your robot, you shouldn't have it overpromise what it's going to deliver, because people will be upset by that. The corollary to this is, don't build a robot that looks like Einstein. If a robot has eyes that illustrate gaze direction, well, it better be the case that that gaze direction is relevant to what the robot's going to react to or going to do. If it looks like it's looking at something but isn't really looking at it, that's going to confuse people. If a robot has emotions, it better change its emotional state in an understandable way, and its emotional state should lead to appropriate changes in actions. So some people, work with emotions in robots, and they make great videos, but is that something that people want to interact with on a daily basis? So making the robot authentic is important. And I'm sorry, Professor Inoue, but there's that thing on the, it makes it look like it's a superhero, and it's not a superhero. The rest is okay, but I know your designs. The ones that were designed in your lab were much more authentic in everything. Yes, and we saw in the video today when your robots were looking at something, looking at the ball, they were chasing the ball. So their head motion actually told someone what it was paying attention to, and that's what it was paying attention to. So it gave the right meaning. Human perception is amazing, and I'm going to show you an example of how designers of products often use human perception without us being aware of how they use human perception, if the system gives them the right feedback. So the feedback needs to be intuitive to understand, and it needs to be unambiguous, and then a person can learn to interact with the machine with almost no training. So I'm going to show you this example. This is a mobile phone app called Word Lens, and it translates. It takes an image and translates from one language to another. So in this case, Spanish to English, but you can get French to English and English to French, etc. Now, so it's an app. You just point the camera at something, and it does the translation. But in fact, the person is really, really important here. Let me show you another video. This has some sound.
So you got a menu that's mostly in Spanish, and it translates. You can see it translates digital special.
So what he's saying there is that the person actually adjusts the image until they get a good translation. You never had to tell them to do that. They just do that. They hold up the thing, and they keep moving the camera until a valid translation pops out. So they're adjusting the camera and getting a good image for free. The algorithm didn't have to be as general purpose as it would if you gave it arbitrary images, because you're making the user do some work for you without them having to be told to do the work. And that scenario can be used in lots and lots of areas for interacting with robots. Let the user do the work that they're really good at, but don't tell them they have to do the work. Let's go to the bigger picture. This is about robots. This is, this is why the solution isn't a robot over there on the hill. Europe in 1950, you see the age profile, women on the right, men on the left, and a total of 350 million people in 1950. There we are in 2000, and there will be in 2050. And you see that the snake swallowed something. It was the baby boomers. So much different population profile. In Japan, it's even more significant, same sort of data. 1950 on the left, 2005 in the middle, 2050 in the right. And why are the more women over 90? Well, that's because it's the women between 90 and 95 and the women between 95 and 100. It turns out, if you want to live a long time, Professor Inoue, it turns out it's great to be Japanese. It's even better to be a Japanese woman in order to live a long time. And it's even better if you're a Japanese woman from Okinawa, it turns out. But you see this complete change in the ratio of older people to younger people. So it's not necessarily that robots will be needed for healthcare, but robots will be needed to do all the tasks that all these younger people used to do, and they're just not around to do those tasks. And so we worry about the pension systems having enough money to pay the older people, but those pension dollars or yen or euros are then going to be used to compete for services from fewer younger people, which will drive up the price of those services. So having robots that can do construction and do farming and other things is, for me, a roboticist, the solution to that. This is the US data in a slightly different form, and I'm right there. This is the percentage of population 65 and above. It's just about, just as we're getting there, Matt. We're the problem. So the world needs robots because of this change in population profile. There's lots of great robotics research around. We've seen that for the last 2 days, lots of humanoids and other robots. But these new robot capabilities are going to allow ordinary people to directly control and program cheap, sophisticated robots. It's going to change the nature of robots and how they're used. And, it's probably not a good idea to use this phrase with robots, but there's going to be new killer apps for robots that we can't yet imagine. In the same way, when the first PCs came out, we didn't imagine Google, having access to the world's databases. And they'll change our world completely over the next 20 years, I believe. So that says, let's invest in robots. And I know there's some VCs in the audience here wanting to invest in robots. But investing in robots is hard. It's tricky to be a robotics investor because it's difficult to tell what is hard and what is easy. Those lines get blurred a lot, and some of it is our fault. It's difficult to predict whether the market will be responsive to a radically new solution involving a robot. And conventional top-down engineering often goes astray in developing robust robotic solutions. So what is hard and what is easy? Well, it's a problem with fantasy versus reality. Science fiction robots are fantastic in that they're fantasies. But people think, oh, I saw a robot in a movie do that. Why can't your robot do what I saw happen in the movie? And some corporate robots are fantastic in a fantasy sense. Unfortunately, some of the robots that companies have shown off in videos have not been authentic in the way they work. They're sometimes made to appear as though the robot can climb stairs or can shake hands with a person, but it's a very carefully scripted video that we've seen. the video doesn't tell whether the capability is robust or not. But this often leads to people astray, and some funding agencies and some government people astray. Think, oh, robots can already do that. Why do you need research money to solve that problem? I saw a video of a company robot that could do that. That's been bad for us, I think. And then lab demos often make non-obvious simplifying assumptions that the researchers are not aware of. They're best. They really believe that they've got a robust solution, but it may not be robust at all as soon as you take it out of the lab. And then it's really hard to do robot perception, and people just don't understand that it's hard to recognize this is a laser pointer, that it's hard to do the stuff that a 2-year-old can do. And so many times I've hired engineers who have not worked in computer vision at all. They look at me as I'm an idiot when they say, why don't you just program the robot to see the chairs in the room and go around, and recognize the chairs? That must be easy. A chair has 4 legs. You just write a program to see the legs. And those of us as researchers know it's an unsolved problem. And 3D data, it's useful, but it's not a panacea. You still have to match and model and do things, but people, many robot investors have said to me, oh, it's going to be so much easier now, you'll just put a Kinect on your robot and your perception problem is solved. It just gives you 3D data indoors. It doesn't solve perception. The second thing was, it's hard to tell whether the world is ready for a new solution. This is Colin Angle, the CEO of iRobot. This is one of his slides. This is 14 failed business models that we had at iRobot before we finally got 2 that worked. Our first one was movie rights for a robotic mission to the moon back in 1990. But we did other things, some which made some money. One of them, this is an interesting one, number 6. We worked with MITI, Japanese Ministry of International Trade and Industry, in the 1990s to develop nuclear power plant inspection robots. We could not get anyone to say that they would actually have a robot in a nuclear power plant. Totally failed business model. Until March 18th of last year, which was a week after the disaster, and we got a call saying, please, send some robots. So we sent robots to Fukushima. Just over a week after it happened, we sent 4 robots. They're still there. The PackBots went in two robots at a time to act as data relays as one robot got further into the reactor. This is a very old nuclear reactor. There were no networks there, so a lot of the sensors are just analog dials. You had to see them. So one robot would go in and point its camera at those analog dials, and then this ad hoc Wi-Fi network hopping to the other robot, hopping back to where people were safe, and the robots went in and found out a lot about the details of what was going on inside the reactor. The larger robots, the 200-kilogram robots, were actually used to move stuff around. And this next one is a photo from Fukushima. They actually rigged it up to be a vacuum cleaner. iRobot still makes vacuum cleaners, even if they're 200 kilogram. So this actually went out and it's still there, and they're with a long hose back from here and on the fly cleanup of a radioactive material. So my point is, some things can be great ideas, but the world isn't ready for them. And we as roboticists say, the robot is the solution over there, but getting people to accept that is a harder problem. And then robotic engineering is different than other engineering in many ways. Conventional, here's something that I would absolutely sign up to do. Make an airplane fly autonomously from Charles de Gaulle to Boston. That's easy. But I would not, with a straight face, take money from anyone, a funder or a VC, and I'll take money from VCs in a blink. But I wouldn't take money for them and promise them that after 3 years, I could get a robot to do this. I certainly wouldn't promise them that a robot could put its hand in my pants pocket. But, so I can do that. We can all do that. We can just reach in there, there's stuff in there, we can feel around, we can pull it out, we can do that. That's much harder than flying from Charles de Gaulle to Boston. And because, flying from Charles de Gaulle to Boston, you've got distinct phases with stable boundary conditions. But in robotics, in an unstructured environment, the boundary conditions are changing every few tens of milliseconds. You have to adjust to new, unpredictable and unmeasurable boundary conditions often. And the sensors don't tell you the whole thing. They give you a sparse projection, which you as an extremist minimalist, Matt, would like, but it's only a very sparse amount of data that you get. So it's hard to do robotic engineering. So there's opportunities, there's barriers. It takes a while. This is the first lab prototype that we built in my lab at MIT of a robot vacuum cleaner in 1992. We weren't real smart about some things. The dirty air was sucked through the main computer system there. But it had lots of features. But it was 10 years to turn that into the first production robot, and another 8 years of refinement to when the robot could deal with tassels on rugs and unwind them and not get caught up. So that's an 18-year project from first prototype to what I think is a good, robust solution out in the world. It takes a while. But academia is also not industry, and there are different measurement systems. And when you make the transition, it often catches people unaware, and if you're working now with a company, you, as an academic, catch them unaware. Both sides are unaware. So the reward systems are very different. In academia, we're rewarded for elegance and novelty of ideas. That's what makes our record. But in the commercial world, you're rewarded for something a customer wants to pay for. Very different. In academia, someone who has lots of new ideas is rewarded. But in the commercial world, new ideas don't help. It's reliability of product. It's sort of the antithesis. In academia, you sort of argue that your idea has lots of applications. A particular technique has lots of applications. In the real world, no one cares about the particular technique that you're using. They don't care that you're using Bayesian systems underneath inside the robot. They just want it to work. In academia, the idea only really needs to interface to a conference paper. And many of them only do interface to conference papers, whereas in the real world, the technique or subsystem has to interface to the rest of the product. And the idea doesn't really actually have to be practical to get good applause in an academic setting, but it has to work and has to be cheap to work in the commercial world. And the artifacts that we build in academia and commercial products are very different. In academia, it just needs to work for the duration of an experiment. In the real world, hundreds, thousands of hours, in storms, in the North Sea, it's got to work. In academia, you have a team of PhD students whose careers depend on it, and they will nurse it along to make it do its piece. The real world, the owner thinks they paid too much for it, and they just want it to work. The interface in academia can be arbitrarily bad. It has to be easy to use in the commercial world. And you get polite applause even for a dumb idea at a conference. No one will buy it unless it provides value in a commercial product. Then there's communication challenges, and I've been on both sides of this. As an academic working with industry engineers, two minutes, and as a CEO having experience working with me as an academic. So what I didn't realize when I started companies is engineers in companies will not read scientific papers. I would go and they'd say, oh, we're having this problem, and I'd give them a bunch of papers, and I'd say, the answer's going to be in here somewhere. And I'd come back a week later, and I'd say, what do you think of the papers? Oh, we didn't look at them. And I realized it's because bachelor's level engineers don't actually ever get trained to read scientific papers. Only master's and PhD level students can do it. And so there's a mismatch as an academic working with engineers in industry often. The CEO, on the other hand, sees the academic, me in this case, and thinks that I have contempt for customers because they don't appreciate how good this robot is. The engineer doesn't care about intellectual debates and academic vindication in the same way academics do. The CEO sees the academic who he's working with as caring way too much about their pet technique and approach. The engineer will only implement what they can understand. If they don't understand it, they won't implement it. the CEO sees the academics being unwilling to compromise, even when the alternative is to shut down the company. And I think there are many companies we can point to where that's been what's gone wrong. And the engineer wants hard numeric specs and will engineer to them. The academic tends to think, this is too complicated to have specs. This is a very complex system, and we can't formalize it down into a few numbers. You'd miss the essence of it if we tried to do that. It's much more than that. So there's a communication challenge. And lastly, there's a difference between what the visionary wants of their product and what engineering needs. So we as academics may have this great idea, we want to turn it into a product, and we don't want it to dilute it in order to get it out the door. But the engineering team who has to turn it into a product needs respect for the process of turning that vision into reality and how it has to change. This is what I call the wrong rock thing. Often the visionary says, no, you didn't engineer that right, but they can't tell what is right. And actually, Steve Jobs is famous for this, and he wasn't even an academic, but he was a visionary. He couldn't say what the right answer was, but he would say, I know what the right answer is when you show it to me. So just giving that's the wrong rock, that's the wrong rock. The engineer says, is this the right rock? Is this the right rock? No. So communication there is a real problem. And lastly, this is what I've discovered over the years. For the vision to be, I want my vision to be understood by the engineering team, even when I can't really explain it. And what I've discovered is I have to have the conversation every single day about what it is that we're really trying to do and why we're trying to do it, and what must be in the first version of the product to deliver on it. So in the case of the Roomba, it was that it had to be low cost. We couldn't sell a high-cost Roomba and have the market adopt it. We had to go low cost, low cost, low cost. How do we get to that? So there's lots of stuff happening in robotics. I think it's the golden age of robot innovation. Exponentials are helping us. We've now got, instead of just one room full of robotic researchers like this, we've got thousands and thousands and thousands of robotic researchers across the world. It's a great age of robot innovation. Turning it into real products that real people use has challenges, and there's communication, and making that switch over is difficult. But I think we'll look back at the early parts of this century as the time when robots came into our lives. And I just feel incredibly lucky to be around for some big transformation like that. It's sort of like being in Detroit, I think, around 1900 to 1910, when automobiles turned into something real. That's what's happening with robots now. So with that, thank you very much for your attention.